On April 28, 2025, at 12:33 CEST, the transmission grids of Spain and Portugal completely collapsed. The European Network of Transmission System Operators for Electricity, or ENSO-E, categorized this as a Scale 3 incident. This is the highest and most severe classification under their framework, triggered by a massive loss of demand combined with a total absence of voltage. This chart plots the frequency of the Iberian grid against the rest of continental Europe. At exactly 12:33 and 19 seconds, the lines violently diverge. This is the precise moment the Iberian grid decoupled from the rest of the continent. Major grid failures are usually assumed to result from a lack of generation adequacy or a deficit of physical inertia. The data shows that neither of those conditions caused this collapse. To understand the failure, we have to look past standard power shortage metrics and examine the physics of dynamic voltage control in the final seconds before the blackout. The investigation revealed that the root cause of the blackout was a failure of dynamic voltage control, triggered by fixed power factors in inverter-based energy resources. This is the official ENSO-E root cause tree. We will use it as our map, focusing on the final outcome, the loss of synchronism. Reading from the bottom up, we can trace this failure backward to the specific hardware behaviors and regulatory rules that caused it. The overarching physical mechanism at play was a severe deficit in reactive power absorption. Reactive power is the energy that maintains voltage levels within a system. Without the ability to quickly absorb this excess reactive power, the grid experienced an uncontrollable cascade of overvoltage disconnections. While the final collapse executed in exactly 83 seconds, examining that time frame requires first understanding the highly precarious state of the grid 30 minutes prior to the trigger. Shifting the timeline back to 12:03 CEST, the system recorded an initial grid disturbance. This data comes from phase measurement units, measuring electrical waves on the grid in real time. The charts show intense signal variance, capturing two distinct oscillatory events echoing across the continental synchronous area. The first event is a 0.63 Hz forced oscillation, localized entirely within the Spanish grid. This oscillation acted as an exciter for a wider event, a 0.2 Hz inter-area mode spreading across the entire European continent. To damp these oscillations, grid dispatchers took manual operational measures. They reduced power exports to France and coupled internal transmission lines in the south of Spain. These mitigations worked, but created a critical physical consequence. Altering the transmission topology inherently increased the baseline voltage across the entire Iberian power system. The Spanish 400 kilovolt transmission grid operates under standards that allow for a wider voltage range than neighboring European countries. This makes it uniquely vulnerable when voltage climbs. As this threshold chart shows, the margin between Spain's normal upper operating limit of 420 kilovolts and the hard 435 kilovolt limit is extremely narrow. If voltage hits 435, generator protections automatically force a trip to prevent hardware damage. The necessary oscillation mitigations, combined with these structural limits, pushed the grid's operating voltage perilously close to the maximum boundary. The system was now fully primed for a localized shock. At exactly 12:32 hours CEST, the rapid degradation begins. Large renewable energy sources across Spain suddenly reduce their active power output by approximately 500 megawatts. These specific inverter-based renewable resources were configured to operate on a fixed power factor. A power factor is the ratio of working active power to apparent power. Operating on a fixed power factor dictates that a drop in active power mathematically forces the hardware to execute a proportional drop in its reactive power absorption. It does this automatically, regardless of what the external grid actually needs. To compensate for this drop in reactive absorption, conventional synchronous generators are expected to dynamically step up, providing the reactive support needed to stabilize voltage. Operational data shows that many of these conventional generators were operating well below 75% of their Q reference requirements. Q reference is the baseline reactive power target set by the transmission system operator. Looking at this capacity chart, we can contrast the massive, inflexible footprint of the fixed power factor renewable units against the much smaller capacity of the dynamic, conventional generators. The only remaining mechanisms available to control the voltage were shunt reactors. However, these devices required slow, manual switching by dispatchers in the control room. Without rapid, automated reactive power sinks to absorb the excess energy, the grid voltage suddenly spiked. The physics of fixed power factors stripped the grid of automatic absorption, and slow manual reactor switching could not compensate in time. Together, they turned a routine 500 megawatt active power adjustment into a lethal reactive power deficit. 57 seconds later, the localized voltage spike first reached a critical threshold in the Granada region. A 400 to 220 kilovolt transformer tripped offline due to its overvoltage protection. This instantly cut off 165 megavolt amperes reactive, or mVAR, of vital reactive energy absorption. This dual-axis chart demonstrates the direct correlation. As the rising voltage breaches the 435 kilovolt limit, it triggers a massive cumulative loss of generation megawatts as protections engage. Tracking the timeline forward to 12:33 and 16 seconds, over 727 megawatts of photovoltaic and thermosolar generation simultaneously tripped offline in the Badajoz area. Looking at the geographic distribution, we map the rapid spread of the cascading failure over 2 seconds, concentrated heavily across the southern and western regions. This includes the immediate loss of an additional 928 megawatts of generation across Segovia, Huelva, and Sevilla. This created a destructive feedback loop. As generators tripped to protect their own hardware from high voltage, the grid lost even more reactive power absorption. That deficit drove the systemic voltage higher. Simultaneously, an exacerbating factor occurred in the low-voltage distribution grids. Thousands of sub-1 megawatt rooftop solar PV inverters also began tripping offline due to localized overvoltage. These localized rooftop trips wildly altered the power flows between the transmission and distribution networks, further blinding dispatchers to the full scope of the destabilization. In a 21-second self-sustaining death spiral, automated overvoltage protections actively destroyed the grid's remaining ability to regulate its own voltage. At 12:33 and 19 seconds, the cascade of disconnections crossed a critical mathematical threshold, stripping the Iberian system of its required synchronizing torque. Mapping this back to the autopsy framework, the cascade lands exactly on this node, the point of no return. The critical AC connection between the Iberian Peninsula and the rest of continental Europe violently severs. The physical consequence of this break is that the Iberian transmission angle diverged so drastically from continental Europe that it triggered the out-of-step protection relays at the French border, severing the physical lines. The sudden loss of massive generation caused the grid's frequency to plummet. This triggered the automatic low-frequency demand disconnection, or LFDD, a defense plan that sheds load to balance supply and demand. The LFDD failed to save the grid because it is designed exclusively to fix active power imbalances. It is entirely powerless to correct a grid that has structurally lost AC synchronism. Once AC synchronism was lost, isolating the Iberian grid into island mode under extreme voltage conditions made total electrical collapse mathematically inevitable. The entire event resolved in exactly 83 seconds. The AC interconnectors to Morocco and France tripped entirely, and all system parameters in the Iberian grid collapsed to zero. The 2025 Iberian blackout carries distinct implications for the global energy transition. The old paradigm relied heavily on the physical inertia of massive spinning turbines to self-regulate. The modern grid relies on complex networks of inverter-based resources. This blackout demonstrates that relying on static regulatory metrics, such as forcing renewables to operate on fixed power factors, is a fatal flaw in modern grid architecture. Surviving the energy transition requires grid operators to move past manual human interventions. Grid security now depends on strict, sub-second automated dynamic voltage control.